In the last module, we had used the fact that the square root of 2 is an irrational number. Let's prove that. Before I begin this proof, let me remark that the proof I am about to give is considered one of the most elegant proofs in mathematics. It is very straightforward and simple, at the same time very beautiful. First, let me make a very precise statement as to what I want to prove. Proposition there is no rational number whose square is 2. So I am not stating that square root of 2 is irrational. We don't even know what irrational numbers are so far. What I am stating is, if you take a rational number and square it, you cannot possibly get the number 2. Let's see the proof. Suppose Q equal to m by n is rational. Okay? Further assume that m and n have no common factors. Well, we can assume that simply because if there is a common factor between m and n, I just cancel it out. I can get rid of all the common factors and put q in its lowest form. Now, suppose q squared equal to 2. So this is going to be a proof by contradiction. I'm going to assume that the result is false and that there is a rational number whose square is 2 and somehow arrive at a contradiction. This just means that m squared by n squared is 2, or in other words, m squared equals 2n squared. Okay? Now what does m squared equal to 2n squared tell us? It tells us that 2 divides m square. This is just means divides. Okay, just this vertical line just means divides. Because the right hand side is 2n squared, 2 must divide the left hand side, which is m squared. But if you think about it, since 2 divides m squared, it must be the case that 2 divides m. Okay? Think about why this is true. If 2 were to divide m squared, there is no choice but for 2 to divide m. But that means 4 divides m squared. Okay? 4 must divide m squared. Why is this the case? Because 2 divides m, therefore 4 must divide m squared. Okay? That means the LHS here is divisible by 4. That means the RHS must also be divisible by 4. Now there is already a 2 coming from 2n squared. Putting all this together, we get 2 must divide n squared. 2 must divide n squared. Okay? Because 2 divides n squared, by the same logic, 2 divides n and hence 4 divides n squared. Okay? This is actually not going to be useful in the proof. All I need is that 2 divides n. Okay? But I'm just making that remark. But that means 2 divides m and 2 divides n as well. What is the upshot of all this? 2 is a common factor. 2 is a common factor for m and n. This is a contradiction. This is a contradiction. Why is this a contradiction? Because we have assumed that m and n have no common factors. Hence, Hence, our proposition is proved. Okay. This is a course on real analysis, and you have just watched the module on the square root of 2.